Last time I have introduced you the distinction between a device, a solar energy device, and the system, and we also found that the performance of the system will depend critically on the component combination. In spite of the fact that a collector may be efficient, unless you have sufficient storage, it will not be able to meet the requirements. Further, we distinguished between the performance which is indicated, let us say, by efficiency over a short period of time versus a long term performance, the time period being a year, because the meteorological cycle repeats itself over a year, and also the economic analysis are based on yearly returns. And last I was discussing about the performance index, which we called the solar load fraction. On a monthly scale indicated by small f, on an yearly scale indicated by capital F, where this capital F will be a summation of weighted averages of the monthly solar fractions with the load on the system every month upon Li. I may be equal to 1 to 12 for the 12 months. So, with a explicit condition Fi, if it is greater than or equal to 1, it should be treated as equal to 1, which translated in simple terms, a solar energy system supplying energy more than the requirement or more than the load on the system shall not be taken into account, and it shall be equated as if it is supplying only the energy needed. Of course, the role of the storage is taken into account, the excess energy will go into the storage, but nevertheless it cannot meet any more than whatever the load is in the system. So, I have shown curves of solar load fraction yearly versus the main parameter being the collector area, and this is 1, it can't be more than 1, and you have got several curves like this asymptotically starting from 0 and going to 1 as area increases. This may be 1, 2, 3, another 4. We try to ascribe the differences. This may be a typical location, typical application. This may be a location where the solar radiation is lesser, consequently my load fraction might is lower, and we also said that though dF upon dAc is positive, the load fraction increases with area, no doubt, but d squared f upon dAc squared with a convex upward curves is less than 0. What it means is the load fraction increases at a decreasing rate as the area increases. Initially, for small areas, it is almost linearly proportional. As you double, let us say a 0.25 square meters and doubled to 0.5 square meters, there is no question of energy being in excess of the demand. Consequently, continuously the load fraction on a day basis or a monthly basis increases, and hence it will be directly proportional to the area. Subsequently, either may be because of non-uniformity in the load or the non-uniformity in the solar radiation, equal incremental areas will not result in equal incremental f, it will be less, which makes it the convex upwards curve, making d squared f upon dAc square negative. That means, f increases at a decreasing rate with area. So, each curve has been ascribed as due to either a lower radiation or a higher load fraction or a higher load, and the features we have already described last time. And curve 3 shows the variation of f with the system when it is provided with a larger storage. So, we need what is a storage size. My performance is going to be fairly critically dependent upon the storage. Say for example, you can have 1 day storage. Of course, the energy delivered will depend upon what is that 1 day, be it December, be it June. Obviously, depending upon the solar radiation that is available, the energy delivered will depend upon the season. And you may typically provide 1 day storage, so that the energy collected over today shall be available for use irrespective of the timing the next day. So, a 1 day storage is typical, and an optimum method one has to go through this. This requires meteorological data, which essentially shows how many cloudy days occur consecutively. So, if for example, if you consider a location like Cherrapunji in the eastern part of India, or even Mumbai, this almost rains 200 days in a year. This will be 3 to 4 months of monsoon. So, you may consider how many days of continuous uninterrupted rainfall could be there. It could be only a day for many locations, or 2 days 3 times a year, and a place like Cherrapunji, it may have 10 times or 10 days consecutively, or 4 times a year. Now, you have to find out an optimum, whether you will provide a simple 1 day storage or 2 days, because it is likely to take care of 3 times in a year when it does not, when there is no sunshine and when it is raining. So, that is an optimization which will depend upon the specific meteorological detail of the location. So, we are curve 4 is a better heat exchanger or a worse heat exchanger. If the heat exchanger has a low effectiveness, it requires a larger delta T. Consequently, it is a penalty on the collector. Right. So, you are asking the solar collector to deliver energy at a higher temperature, much higher, if the load heat exchanger is poor, and hence the collector will be operating at a lower efficiency, and hence you have a higher curve or a lower load fraction met by particular system. So, now if you really want to summarize, we want a system performance which includes all the components like collector, storage, heat exchangers, and interestingly load and its distribution. This does not come explicitly in the curves I have described, but I shall illustrate this fact. Suppose you have got 12 gigajoules of load in a year. This can be 1 gigajoule every month or non-uniform with max like 2 gigajoules in December and a minimum like 0.2 gigajoules in June. Alternately, you may also have max 2 gigajoules in June and min 0.2 gigajoules in December. So, you need not take them literally. By choosing June and December, I essentially mean the highest radiation and the lowest radiation, matching with the highest demand and not matching with the highest demand. So, consequently, your load fraction, it shall not be able to save the energy or the load that is met with or the energy delivered when the excess radiation is there, when there is no demand, but in the case of when it is unable to demand, you have a penalty. So, if my solar radiation, if this is the month, is typically like this, January to December, and my load is following the solar radiation, I can expect this is load or solar radiation. So, my F will be higher compared to a situation like this, where you have of course, the same variation of the load, solar radiation sorry, and with the months, and my load is can be like this. Low load when the radiation is maximum and a higher load when the radiation is lower. Okay. So, this will be adverse compared to the previous curve I have shown. So, the total load on the system in 1 year may be the same, but if the distribution is different, my effective performance is going to be different. This is one thing we have to keep in mind in designing the solar energy system. A solution could be optimize by F the solar load fraction being highest per unit investment, or alternately combine different applications depending on the season. Typically, if I have a air conditioning in summer and space heating in winter, my total load fraction will improve enormously if I can do both with the same system. So, whatever we were talking about the system and the components, if we try to make a small summary, they are broadly classified as active and passive systems, though there is no hard and fast demarcation, and a single efficiency needs to be replaced with sort of performance index which we will call the solar load fraction, which may be defined on a monthly basis or an yearly basis, where yearly value will be weighted average of Fi Li upon Li, I is equal to 1 to 12, where Li are the load for each month and Fi are the corresponding load fractions. So, that is what we are rating is the load fraction, and this solar load fraction increases with the collector area, but at a decreasing rate. So, this feature d squared f upon d A c square less than 0, d f by d A c though is positive, has a bearing on optimum collector array area. So, this nonlinearity tells us, rather gives us a clue that we need not rather try to replace an existing conventional system with the solar energy system, but use the solar energy system such that you will have the maximum energy delivered per unit investment. Okay. If you spend 1 rupee and you should be able to get so many joules, which will be the highest for that particular combination. The issue is not whether you are meeting all the load or not, but a fraction of that load is being met at the highest or rather lowest investment. Now, all this thing points to something else. If you put a solar energy system in Chennai, South India, or Delhi, North India, for the same application, the performance is not going to be the same. The energy delivered may be comparable or can be proportional to the solar radiation in one sense. Nevertheless, considering the fact that the ambient temperatures are different, and if you consider a heating load or a cooling load, they will be entirely different. Consequently, effective solar load fraction for the same area, for the same collectors will be different at different places. So, what we noticed is you need long term performance and this depends upon the location, because my load is distributed according to the particular location under consideration. So, this makes it interesting as well as challenging. So, one simple efficiency multiplied by some sort of input is not an indication Okay? So, unlike a conventional fan or a generator or any other machine, it is not efficiency multiplied by input. Your overall effectiveness depends upon the load, the climate, and of course, your collector performance, along with the other components like storage, heat exchangers and controls. So, a given collector shall not be equally effective at every place, but it will depend upon so many points. So, we need to have a design procedure or optimization procedure depending upon the load, depending upon the location, which calls for either a simulation for each location or maybe experimental. Validity. We shall come to the advantages and disadvantages and the information, these things that reveal if you do an experimental study or a simulation. We also realized we need long term system performance. I am deliberately avoiding the word prediction of long term system performance, because some people get confused and say what is going to happen tomorrow or day after. It is not that type of a prediction we do, but it is an estimate of a typical system that is likely to deliver so much of energy for a typical climate of that particular location under consideration. When we do according to certain modeling, you can arrive at whether a collector A with a certain orientation is better than a collector A with another orientation or another collector B, and the storage says. So, you can optimize, for example, storage, heat exchangers, control, and so on and so forth, depending upon the component, and it may be even the slope, flow rate, etc. Right. So, there are so many variables based upon which your effective system performance is going to depend, and we said that single efficiency determined is an indicative of the performance of the solar collector, but its effectiveness in meeting the load will depend upon not only the climatological data, but also the load itself. To illustrate the point, I may have 12 gigajoules distributed equally 1 gigajoule every month, but the other way around is all the 12 gigajoules occur in, say, December or maybe June, any one month. So, this is likely to have a higher effectiveness for a given area than this particular distribution, and this is likely to be better than what it would be in December. So, not only the quantum of the load, but its distribution also plays an important role. Sometimes the system may be, it may be fortunate for us, in the sense that if the demand meets the solar radiation, in general follows the solar radiation. In other words, I have a higher demand in summer and lower demand in summer, winter, then you will have a better performance index rather than the other way around. So, what we try to do is we play on this non-linearity. So, this is F and this is area. I would like to pick up the best area though we will come to it economics if time permits a little later. I will call this ordinate as LCS, which is life cycle savings. In simple terms, this is the amount of money that the solar energy is going to save in its lifetime. It may be 10 years, it may be 15 years, it may be 20 years, whatever the life is, and this is the area AC. So, it starts with negative and this is positive. In other words, when area is 0, I think he may be little naive. He bought the heat exchangers, the storage tank, site preparation, everything, but did not put any collector. Consequently, all that cost will give rise to a negative life cycle savings. Life cycle savings in simple terms can be defined as, in the lifetime of the solar energy system, how much is the amount of money that it is going to save. So, you have to take into account the investment, interest on the investment, and these are all expenses plus the maintenance, but what is your credit side is the saving of the fuel, and if this is high, then compared to the expenses, then you have a positive life cycle savings over a period of 20 years. One can take, depending upon the reality of the situation, the inflation in the oil price or the conventional fuel price and the depreciation of the system and the interest that you pay for the amount invested in initially installing the system. So, this is a complete economic exercise which will ultimately give you, if the collector system is going to operate for a period of 10 years, you are going to have a net profit or net savings of so much. So, when the area is 0, but you have spent money on the other components, you will not have any life cycle savings, a negative life cycle savings only. So, as this area increases, this life cycle savings increase. Now, as the slope d squared f by d s squared is negative, in other words, incremental areas are not resulting in proportional increase in the solar load fraction, my life cycle savings start dropping. So, this may be the point where I have maximum savings. So, this is my AC optimum and this may be F OPT. So, you combine the solar load fraction curve versus AC with the life cycle savings or any other economic curve, and you pick up where you are going to have the maximum savings. In order that the idea is not to replace an existing system, but use a solar energy system such that my returns are the maximum. So, this is how it is done through the combination of life cycle savings versus the solar load fraction. Why I had to get into this economics a little bit here is, we need this F, which will be a function of the area mainly, and other parameters like operating parameters. Plus your load and the distribution. This is an important feature of solar energy systems in particular and in general of environmentally driven systems. So, what we try to say is, I have already demonstrated 12 gigajoules uniformly distributed is not the same thing when 12 gigajoules occur over a month or even a day, though the total yearly load appears to be same. So, we somehow try to optimize making use of the nonlinearity of the F versus AC curve, so that my investment made yields the maximum return per unit investment. So, it should be based upon the long term performance, and then that performance is depend upon the location, the load and the load distribution. Consequently, F is not simple to evaluate, like efficiency multiplied by input. So, this is not on. So, how do we get this F? The subject matter now is the long term performance. By long term performance, we intend that the performance of a solar energy system over a period of 1 year. You may make a monthly calculation, you may make a hour by hour calculation, and or conduct an experiment putting up a system on the actual site or wherever is possible, and then monitor for a year or so. If you do that, if you conduct the experiment for one particular area, you will get 1 point, and the time needed is experiments. Let us say first. For the system scale, not only they are expensive, one single area will give me one single point. Then in order to save time, you may do the experiments with area AC1, AC2, AC3 like that, and I may be able to get a few points. Okay. So, I can join and get this F versus AC curve for, let us say, one location Chennai, right. Now, if you want it for Delhi, so you have to redo the experiment in Delhi, which is prohibitively expensive, and it will take also the time. Okay, even if you are concentrating only on a certain location and somehow save time by putting up 10 systems of different areas and found out that the solar load fraction versus the area curve was whatever I have depicted earlier for Chennai. And somebody smart can say what is the effect of beta. I will change the slope. What is the optimum slope? Then similarly the flow rate and control strategy, which we shall come to it a little later. So, for each one of these variables anything or heat exchanger size. So, you have to keep on doing experiment by experiment, which is not only expensive, but also a time taking to do system scale experiments. Now, it is not that we are theoreticians and trying to run down the experimental procedure. Experiments are important. A, to demonstrate the viability. Yes, before you embark on economic viability, you should say, you should prove that the system works. So, the experimental can establish the viability of the system technologically. B, it will reveal the practical difficulties and performance. For example, the practical difficulty could be even transport or monitoring of the system, and the performance, though your solar load fraction, actually you can calculate, find out what is the energy delivered compared to the what is the energy that is met by the load on the load. So, this performance, what I mean is, are there leaks in the collector or the pipes, or if it is evacuated, loss of vacuum, and deterioration of absorption or transmittance, etc. For example, if you have got a black painted surface with tube and fin type of absorbers, which we have discussed in detail, it may so happen over a period of 6 months or 8 months, the a black paint may peel off or may not have the same absorption that we have had at the beginning. Similarly, the transmittance, though not of the glass covers, if particularly if plastics are used, they are not UV stable. Consequently, your transmittance suffers, deteriorates as time proceeds. So, we would in turn say that system scale experiments are not always feasible on account of the time involved in the expenses. Also, the results obtained at one location are not valid for another location. Further, influence of changes in design conditions cannot be easily assessed. But this is not to say that it is not necessary. It is only the system scale experiments that can reveal the practical difficulties that in a system may encounter. For example, if you consider a control, so that TFO is greater than TFI, outlet temperature from the collector is higher than the inlet temperature. How much? By 1 degree, 2, or what? So, if you put the thermostat in the control, actually you will find that it is turning off or turning on the pump with a 5 minutes or 5 degrees of bandwidth, compared to another control which may have a bandwidth of only 1 degree. Okay. So, which one is better will depend upon again your utilization and applicability. If the plus minus 5 is valid, it means that the pump will not be turned on, maybe unless the outlet temperature is more than by 5 degrees of the desired temperature, and it will not be shut off even when it is less by 5 degrees. So, you may be not pumping at the right temperature, waiting for a still higher temperature, and pumping at times at a lower temperature than what is desired. The first one leads to a loss of efficiency, the second one leads to loss of quality of the energy delivered. So, how do we solve this problem of time, expense? At the same time, we would like to have a answer for a system that is optimum for a given application and location. Simulations. Seem to be an answer, that is, you develop component models, like for example, for the collector, So, useful energy gain from a collector is ACFR into IT tau alpha minus UL times TFI minus TA. I have the weather data file and process it to calculate IT tau alpha and estimate UL by the methods we have described for the conditions of operation, and then multiply by of course TFI minus TFO and TA, and I keep on adding this QU over the year, sum it up, QU hours, all hours, okay, from 0 to maybe 365 into 24. Then I will also take care of the fact whether the load is higher than QU or load is less than QU at every instant or a day or a month. Then finally, compute this F. So, with then I may have to add other component models, like for example, a tank, storage tank. If m is the mass of the water in the storage tank, not the mass flow rate, it is the mass, this should be equal to QU. So, the rate of increase of energy inside the tank should be equal to whatever is given by the collector. Likewise, I can model loss in the pipelines, tank and heat exchanger effectiveness, etc., and ultimately come out with my solar load fraction for the year. So, when once you have the component models and coupled them as per the need, it is a simple job, can change location, slope, even if you want even the azimuthal angle, storage size, etc. So, all the variables that are involved, I can just once the complete linking of the simulation of the system model is complete, we can change the we can make a simulation for Chennai, we can make a simulation for Delhi, Srinagar, Simla, Darjeeling, whatever locations you want, and then find out the best beta for that particular location. Either you independently optimize or maximize the solar radiation falling, or we will be ultimately going through the solar energy system performance, because the excess radiation at times may not result in higher load fraction improvement if f is already equal to 1. So, we might just go by f optimization. Then similarly, azimuthal angle, if you are talking about in general a solar collector, azimuthal angle may be equal to 0 is the best solution, that is south facing in the northern hemisphere, or if it is a window where you do not have a control, you might change gamma or to either gain maximum energy or not to gain lot of energy, like in tropical climates. And storage, of course, I have already emphasized the importance of the size of the storage. So, this we have already gone through. The components are coupled with appropriate linking modules. Simulations in general require a detailed metallurgical database and fairly large computing facility. Of course, they are much cheaper than your what shall I say, experiments, and you can use simulations for large and in general non-standard systems. This looks like a sweeping statement. Let me elaborate a little bit. By large system, what I mean is the expense involved is very high, like for example, a power generating system. And a non-standard system means it is not just run of the machine or run of the mill, where you need 60 liters of water for bathing or domestic application, something like this, but then it may be an industrial application which will be requiring larger quantities, which do not have the standard components. So, if you do a simulation for a large non-standard system computation systems, then computational cost is justified. So, we should also understand, even though the cost of simulation is a fraction of the experimental cost, cost of simulation can be significant if you are talking about a small scale system. For example, a domestic water heating system supplying about 60 liters a day may be approximately Rs 20,000. Okay. Now, if you want to simulate, including the computer time and the time money that you pay to the expert or the skilled person, it may be simulation may be 5,000. Let us say a very modest figure, right? And this 5,000 compared to 20,000 is 25%. If this 20,000 is economically viable, 25,000 may not be economically viable. Consequently, if you have a standard system, you would like to have a simple method instead of going to the simulations, which ultimately may come out with a area requirement of 1.78 meter square, or you may have a module of 1.5 meter square standard or 2 meter square. Whether you put 2 meter square at the rate of this 20,000, this additional 5,000 gets justified. You do not need to go through this. 1.5 of course, will be cheaper. Consequently, again if it is a small system, you may not want to go through simulation, particularly if they are standard systems. The other thing that we need to mention in the same context is, unfortunately or fortunately, simulation cost is not proportional to cost of the system. If instead of 60 liters you want 600 liters, it may be multiplied by 10, 2 lakhs. With some scale economy, it may be even less than that, but simulation cost and the time of the computer is going to be exactly the same almost, or whether the area is 60 square meters or 60 liter system or a 600 liter system. So, this is one thing we have to keep in mind. So, once again we may have to also say that simulations require skill of experts. So, the person should be knowledgeable in the area of solar energy, and of course, the how to run the computer simulations. So, this is going to be a little expensive. If a system is to be simulated and you hire a consultant, you have to pay for him, and if that is going to be a significant portion of the system cost, then one has to think about simulations, and it cannot be done routinely by the industry. So, these things of course require component models, though it is a term technical sounding. It is nothing but whatever we have written for Q for the collector or the energy stored in the tank. These are the component models. And if you take for example, a pipe and you estimate the loss as the surface area multiplied by effective heat transfer coefficient and a delta T, that will be the model for the pipe, and the length of the pipe is going to determine how much losses are going to take place. So, we need the component models, and sometimes it is complicated. You have to develop the component models depending upon the component that is being employed. So, we shall have go through the different methods of long term performance prediction by the either experiments or the simulations, and is there a simpler method in the next lecture. Thank you.